In this video, we're going to review some of the gas laws that we learned in Chem 1, and then look at some different calculations that we can do with these. So in terms of gas laws, our first one is Boyle's law, which states that for a given mass of a gas at a constant temperature, the volume of a gas varies inversely with pressure. So remember, inverse means when one goes up, the other goes down. So in this picture, we have two pistons with the same number of particles and a constant temperature we can assume. The volume in the one on the right is decreased, which makes the particles closer together. They collide more often, which will increase the pressure. The formula for Boyle's law is the P1 times V1 is equal to P2 times V2. So remember, when one goes up, the other will go down. Our second one was Charles's law. This states that for a fixed mass of gas at a constant pressure, the volume of a gas is directly proportional to its Kelvin temperature. So here we have two pistons that have a weight on top. The piston on the right is at a higher temperature than the one on the left. The particles are moving faster, and it actually pushes up the piston and expands. And whenever it says that they're directly proportional, means that they go in the same direction. So whenever you increase temperature, it also increases volume. And do note that this is related to its Kelvin temperature, so temperature should be in Kelvin. The formula for this is V1 divided by T1 is equal to V2 divided by T2. And remember, those temperatures must be in Kelvin. The third one we learned, Charles's law was used to determine the temperature of absolute zero. We know that absolute zero is at 0 Kelvin. Kelvin is a scale based off of absolute zero. They actually tested this using different temperatures and volumes of gases. Gases cannot have a negative volume, so there's no possible temperature between absolute zero, which is how they tested this out. Our third gas law that we learned was Guy-Lussac's law. It states that for a given mass of gas at a constant volume, the pressure is directly proportional to its Kelvin temperature. Yet again, directly proportional. When one goes up, the other will go up, and temperatures are yet again in Kelvin. So here we have two containers of a gas that are both 1 liter, so same volume. The one on the left is at 150 Kelvin, and our pressure is 1 atmosphere. The one on the right is heated to 300 Kelvin, which is double the temperature, so therefore our pressure also doubled, now to be 2 atmospheres. Our formula for this is P1 divided by T1 is equal to P2 divided by T2. And yet again, those temperatures are in Kelvin. So these three are not on your reference sheet, but remember, these are all included in our combined gas law. So our combined gas law has your initial pressure times volume divided by temperature in Kelvin is going to be equal to your final pressure times volume divided by temperature in Kelvin. Remember that all three of those gas laws can be found in this combined gas law, but this is not on your reference sheet, so you do need to remember the combined gas law. We had also talked about Avogadro's law very briefly. Avogadro's law states that equal volumes of gases at the same temperature and pressure are going to have the same number of particles, therefore the same number of moles. So whenever we use this, we have the initial volume divided by the initial number of moles is going to be equal to the final volume divided by the final number of moles. So if they put more air in a balloon and add more particles, the volume will increase because the particles increased. Then we came to our ideal gas law, which is the PVNRT, the P times V equals nRT. This one is on your reference sheet for your use. And remember the parts of this. So pressure is P. It can be in any unit most commonly it's going to be in atmospheres or kilopascals. Volume, and volume will need to be in liters. You should not be able to substitute milliliters. Our N is our number of moles, so make sure that it is in moles and not mass. And then remember, our T is still our Kelvin temperature for all gas laws. Now that R, remember that R is our gas constant. And on your reference sheet, it does give you several versions of R. The most commonly used one is the 0.08206 liters times atmosphere divided by moles Kelvin. So this is the one that you would use for atmospheres, which is going to be more common. If the pressure unit is different, you should use a different number for R. So here's several examples of all the gas laws. We're going to walk through 2 of them together, and then the others will be here for you to practice. Feel free to pause the video and try these on your own if you feel comfortable with gas laws. If not, continue watching, and we're going to go through the first one and the third one. The second, fourth, and fifth you can actually do on your own. So looking at the first one, says a sample of gas at 3.0 times 10 to the third millimeters of mercury inside of steel tank is cooled from 500 degrees Celsius to standard temperature. What is the final pressure of the gas? So here it only gives us pressures and temperatures. So we're going to have P over T. Look at our beginning numbers. It tells us that we have a gas at 3.0 times 10 to the third millimeters of mercury, and it starts at 500.0 degrees Celsius. So that's our beginning, P over T. And remember, temperatures have to be changed to Kelvin, so you have to add 273 to the initial number. To find our final pressure, we don't know the final pressure, but we know that the final temperature is standard temperature, which remember is 273 Kelvin. So you can cross multiply to solve this, and you find that that second pressure is going to be equal to 1060 millimeters of mercury. Moving on to the third question. It said, at what temperature would 0.650 moles of nitrogen under a pressure of 175 kilopascals occupy 8.90 liters? So here it actually gives us moles. It also gives us pressure and volume, and it wants no temperature. So the equation that has all of those is the ideal gas law, the PV equals nRT. So make sure that all of your units match. So if you don't know the R value for kilopascals, you need to make sure to convert into atmospheres or a unit that we know. So I did that first. We did stoichiometry, and 175 kilopascals divided by the standard pressure in kilopascals into atmospheres is going to give you that our pressure is 1.73 atmospheres. Next is our volume. It told us that was 8.90. That's equal to our number of moles, which was 0.650, times our R, our ideal gas constant, which with atmospheres is the 0.08206. And then we're looking for temperature. Whenever you're solving for temperature, divide by both the 0.650 and 0.08206, and you get that that temperature is 288, and remember those temperatures are in Kelvin. So if you took time to try the other 3 problems, here are the answers to them. So feel free to pause the video, try each one of these, and see if you get that correct answer or very close to it. Feel free to check with me if you want to see the work for it. I have that in my notes. Let's look at one other thing that you'll be asked to do with gases. This one is actually new. So we're actually going to look at finding the density of a gas. So our problem says, what is the density of chlorine gas at 23 degrees Celsius and 0.941 atmospheres? Now, we haven't talked about any gas laws that deal with density, but density, if you remember, is equal to mass over volume. So we know about Pivnert, the P times V equals nRT. Density is equal to mass over volume, but we can't really figure out a way to plug that into our equation yet because mass is not in PV equals nRT. If you look on your reference sheet, you also have this mole is equal to mass over molar mass that we actually use doing our thermo calculations. So using this, you can substitute moles over molar mass, or mass over molar mass, in for moles in Pivnert. So then we have P times V is equal to M over MM RT. You can rearrange that to try to get to density. So to get to density, we need volume below mass. But first, we have to get rid of molar mass on the bottom. So we can divide by volume, multiply by molar mass. So that gives us pressure times molar mass is equal to mass over volume times RT. The mass over volume, you can substitute for density. So we have a converted equation. So this is PMM equals dirt. So pressure times molar mass is going to be equal to density times R times T. So now using this converted equation, we can solve for density. One thing to remember is that chlorine is diatomic, so it is going to be Cl2, so we have to account for that whenever we plug in that molar mass. So it tells us our pressure is 0.941 atmospheres. Our molar mass for chlorine, remember chlorine is 35.45. If you double that, it is 70.9. Equals, we don't know density. Our R value, since we're in atmospheres, is the 0.08206. And then our temperature, remember, has to be in Kelvin. So do the 23 plus 273, and we get that this is 296. So if we divide by everything on the right, we get that our density is equal to 2.75, and our units are grams per liter. Now you can look at the units and make sure that they do cancel, or just remember that density is in grams per liter, and trust me on it. Definitely practice with this newly converted PMM equals dirt. That is going to come up for sure, and it is something that is brand new that you've never done before.